In this presentation, we're going to go through the response of prestressed concrete members to flexure. By the end of this presentation, I want you to be able to explain how compatibility, equilibrium, and constitutive relationships can be used to calculate the response of a section to combined moment and axial loads. Explain and illustrate the layered section approach or analysis approach. Use response 2000 or a given Excel sheet to construct moment curvature responses of sections with combined moment and axial load. Explain and illustrate the rectangular stress block approach for finding moment curvature relationships. Use the rectangular stress block approach to construct moment curvature responses for sections with combined moment and axial loads. Modify the above procedure to include tension stiffening. Interpret beam behavior from a moment curvature plot. Modify the above procedures to include long-term effects, and calculate deflections of a beam given its moment curvature response. Flexural members are the most widely used prestressed concrete elements. They often have no axial load other than the prestressing force, but will develop procedures for general cases. Typically, we'll have a beam, and in this class, we'll typically work with simply supports, so pin roller support conditions, and some type of loading that causes moment in the beam. We can have areas of our steel and area of non-prestressed steel and area of prestressing steel in the section as well, and we'll see how we can account for both of those. The previous case we looked at was pure axial force, and when we have a pure axial force, we have a constant strain distribution across the depth of the section, so zero curvature. Now when we have bending and we add in bending, we're going to get a strain differential across the depth of the section from our flexural stresses. So you can see we'll have a different stress at the bottom than the top, which gives us a curvature across the section depth. The curvature here is just the slope of our strain profile. Note that in general and in this section, we're going to assume plane sections remain plane, which means we have a linear strain profile across the depth of the section. If we assume that plane sections remain plane, then we only need two variables to define the strain profile across the depth of the section. Typically, we can either use the top strain and bottom strain, or we can have the curvature and the strain at the centroid. So the curvature of the strain profile and the strain at the centroid. Using these, we can calculate the concrete strain at any distance y from the centroidal axis using this equation here. We can find the strains in rebar at any level of the rebar. And we can also find the strain in the prestressing tendons using the equation shown here, with this delta epsilon p being the locked-in strain differential that we talked about in the previous module. Note that the above relationships here assume that curvature is positive when the beam is concave up, meaning that when it's deflecting downward. So that is a note on our sign convention throughout this module. Our equilibrium conditions we can define based on the information shown on this slide. Here we have our cross section, we have our strain profile, we have our stress variation in our concrete across the section depth, our stress in our steel, and our stress in our pre-stressing. So our equilibrium conditions, we need our external applied moment or external applied load N equal to the internal force components. So our concrete stress integrated over the area, our steel stress integrated over the steel area, and our pre-stressing stress integrated over the area of our pre-stressing. So internal forces equal external applied loads. With our moments, we need our external moments to equal our internal moment components. So here we need to integrate our stress times a distance component from the centroidal axis integrated over the area of concrete, same for steel, and same for pre-stressing. If you can remember back to when we talked about axial loads, we could simplify this and just take our stress times our area because we had a constant strain profile across the depth, which means we have had a constant stress profile across the depth. Here, when we're including our moments, you can see our stresses are going to change across the depth. So for now, we'll keep these integrals in our equations. Note also that we can include our post-cracking tension in concrete using tension stiffening, which we'll talk about on the next slide. We can include the post-cracking tensile stresses in the concrete using our tension stiffening equation, just like when just like in our axial loaded members. So we'll use the same equation. The difference is the area that will include tension stiffening effects. So we have what's called an effective embedment zone, and this includes a distance 7.5 times the diameter of the bar or pre-stressing strands to the edges of this effective embedment zone. So here in the figure shown, 7.5 dB to the top would be the top of the effective embedment zone, and we're assuming that 7.5 dB is greater than the distance between the center of the strands and the cover. So the bottom of the beam is the other boundary for the effective embedment zone. So in this zone, we would include tension stiffening. So we'd calculate the post-cracking tensile stresses using the tension stiffening equation, and then include them in our concrete stress diagram within this effective embedment zone. Once again, we can use our equilibrium, compatibility, and constitutive relationships to predict our response. And essentially, we would get down to our two equations that we saw on the previous page. An axial load equal to our stresses in terms of top and bottom strains, and moment in terms of stresses dependent on the top and bottom strain. Essentially, what we would do is it would be a trial and error approach. We would have a given combination of axial load and moment. We would select a value for our top fiber strain. By trial and error, we'd find the bottom fiber strain such that the axial load corresponding with this bottom fiber strain would equal the applied axial load. We'd calculate the corresponding moment, and then we'd see if that moment that we found with this combination of top and bottom fiber strain equals the given moment. If not, we need to go back and change our top fiber strain and try again. If it did, then we know our values for our top and bottom strain, and we could move forward and calculate all of our stresses and forces and moments. It's difficult to work with this approach with closed form equations and integrals. So there are two main approaches that can be used to analyze our flexural sections and develop a moment curvature response. The first is a layered section analysis approach. We'll talk about that, but it's a difficult approach to do by hand. So it's mainly used in computer programs, and you can actually develop your own Excel sheet with some macros to run a layered section analysis approach. The rectangular stress block approach laid out in Collins and Mitchell's textbook we'll go through. And this is another way that you can find the moment curvature response by hand, actually. So it's a simplified approach, and we'll go through this one as well. In the layered section analysis approach, what we do is we idealize the cross-section as a series of rectangular layers. So you can see we have our cross-section, we have different shapes, but we break the cross-section into a series of rectangular layers throughout the depth. We need to assume that the strain in each layer is uniform and equal to the actual strain at the center of that layer. So here you can see that each one of these layers we're assuming has a constant strain across the depth equal to the strain at the centroid of that layer. And then you can see we can use that strain to calculate the stress and the average stress in that layer. And then we have a series of stresses and kind of these stress rectangles. So it's easier to integrate the stresses and find the forces and moments across the section depth. On the next couple slides, we'll go through some of the properties that we'll need to find in each layer. The first is the layer area. So each layer is going to have a width and a height. To find the layer area, we just take that width times the height. If we have a change in cross-section, then we just use the average width across the height of the layer. We can also have the pre-stressing strain, which we can find just using our strain in the pre-stressing and the locked-in strain differential, delta epsilon p. We can find the concrete strain, steel strain, and pre-stressing strain based on the strain at the centroidal axis, the curvature, and the distance between the centroidal axis and the layer of interest. So we can find the concrete strain at each individual concrete layer, at each steel layer, and at each pre-stressing layer. The only difference between the pre-stressing layer and other layers is we have our locked-in strain differential, delta epsilon p, that we need to include. We can find the curvature based on our bottom and top fiber strains and the overall height of the section, and the centroidal strain based on the strain at the top, the curvature, and the distance between the centroidal axis and the top of the section. We can use appropriate constitutive relationships, stress-strain relationships, to relate the strain in the concrete, steel, and pre-stressing to the stress in the concrete, steel, and pre-stressing. So at this point, we would have the stress in each one of our concrete, steel, and pre-stressing layers. Then we can integrate approximately using our summations, where our axial load is just the summation of all of our stresses times our concrete layers, stresses in the steel times the steel layers, and stresses in the pre-stressing times our pre-stressing layers. The moment can be approximated similar with the summation here, where we take the force in each layer times the distance component for the layer, and then similar, so do it for the concrete, do it for steel, and do it for pre-stressing. And then we would have our N prime and M prime to move forward with in the analysis procedure that we laid out a couple slides ago. This is a difficult process. So like I said, you can develop your own Excel sheet. You'd have to likely use macros to be able to develop this procedure. There are also some available programs that we can use. The one that I'll be highlighting in this class is a program called Response 2000 that you can download free online. So we'll talk about this program in our first example problem. Our first example problem will be to use Response 2000 to develop a moment curvature plot for the rectangular section shown here. At this point, you can pause this video and go to the accompanying video for example problem 1. Using Response 2000, we can develop a moment curvature plot for the section on the previous slide. And we can develop moment curvature plots for any type of section with any reinforcement and with different applied axial loads. So you can see that the curve here looks pretty similar to other reinforced concrete moment curvature plots. The difference is you can see that the intercept at zero curvature is under a positive moment. So we have a negative curvature under zero moment, which means the beam is deflecting upward when we have no applied moment. So this is the effect of the pre-stressing strands that cause an upward deflection called camber. So there needs to be some kind of applied moment until the beam gets back to zero curvature or no deflection. And at this point, it would have a positive deflection or a downward deflection. We can also get from the moment curvature plot the maximum moment, and we can also see and gauge and get some idea of the ductility of the section. So we can see, get the ultimate curvature and compare it to the yield curvature to get the curvature ductility and see how ductile our section is. Another approach for analyzing our pre-stressed concrete member for flexure is using the rectangular stress block approach. You may remember the rectangular stress block approach from our regular reinforced concrete analysis, and the same approach is valid for pre-stressed members. The one that I'm going to show you on the next couple slides is a way to use the rectangular stress block approximations to find the full moment curvature behavior. But you can see it's pretty similar to the ACI approach that we would cover in a normal reinforced concrete class. So if you remember, the rectangular stress block approach in general, what it does is we approximate the concrete stress profile over the depth, which would curve here. We approximate it with a rectangular stress distribution. And essentially this rectangular stress distribution needs to have the same area and same centroid as the actual stress distribution in our concrete. We can include tension stiffening if we want for our concrete stress, and we can also include our steel stresses for our non-pre-stress reinforcement and for our pre-stress reinforcement. Collins and Mitchell give us approximate equations for our beta 1 and alpha 1 dependent on the strain in the concrete at ultimate strength. So this epsilon prime C, which may also be written as epsilon naught, and the top fiber strain in the concrete, so epsilon C T, or the tension fiber strain. So with those, we can find our beta 1 and our alpha 1, and with these values, we can determine the compression block, or the compression force in the compression block. We can use these then to find all of our axial loads and moments using some of the same relationships that we already talked about. Now we'll turn to our next example problem where we'll use the rectangular stress block approach to find the moment in curvature for a specific point. So when our top fiber strain is equal to negative 0.5 times 10 to the negative third, with no applied axial load. And then we'll go in and develop a full moment curvature plot. We're going to use the same section that we looked at in example problem 1, and we'll look at how we can also include the tension stiffening effects. So at this point, you can pause this video and go to the example problem 2. If we consider tension stiffening, we need to remember that concrete will not be able to carry tension across a crack. So if you remember back to our axial load discussion, we have our average condition considered over a length or the entire length of the member, but we also have our local conditions at a crack. So our average conditions, we can include the effects of tension stiffening, but at a crack, we have no concrete contributing to the strength. So we'll have a different force in our pre-stressing strands and in our non-pre-stress reinforcement crossing the crack that we need to account for. So essentially, we need to make sure that the strength that we find from the pre-stressing and the tension stiffening component of our concrete strength needs to be less than the yield strength of our tension steel, our pre-stressing and non-pre-stressed tension steel. We can determine this by comparing the curve without tension stiffening to the curve with tension stiffening. So here you can see this dotted line would be the moment curvature curve of a section without tension stiffening. And the solid line up here would be the curve with tension stiffening. Essentially what we need to make sure is that we impose an upper limit on our curve with tension stiffening equal to the maximum capacity without tension stiffening. So you can see right here would be the maximum capacity of the section not including tension stiffening. So this would be the upper limit for our moment for our curve with tension stiffening. So then when we have our section with tension stiffening, we would follow the curve and include tension stiffening until we hit that upper limit, and then we just transition over, or we'd stay on that upper limit. On the next few slides, we're going to go through essentially an example where we find the moment curvature curve for the single T section shown here. And we analyze the curve and see what different aspects of the curve mean on the actual behavior. So you can see the curve, we should have all the properties shown here that you can analyze the section for yourself in Response 2000, but I'm not going to go through that as an example in this class. Using Response 2000, we can find the average condition, including tension stiffening, and the conditions at a crack, or local conditions, not including tension stiffening. You can see we can find the top and bottom fiber strains, which allows us to find our curvature, and the moments that corresponds to each one of these points. You can see I laid out some of our some comments on some of these different points, and you can see because we have such a wide top flange, we have rupturing of our strands as we increase our curvature. Here is the moment versus curvature plot for the section that we saw a couple slides ago. You can see on this side, we have our concrete crushing on the bottom face, controlling our capacity here with a negative moment and negative curvature. Here, the concrete is cracking on the top face from that negative moment. As we kind of work our way up here, we have zero curvature when we have an applied moment of around 600 kip feet. Then our concrete cracks on the bottom face at this point, and we start to go nonlinear. And then as we go nonlinear, here we'll start to see some of our strands rupturing. So our strands, we assume, rupture at a strain of 0.04. So we have rupturing of 2 strands, 2 more strands, and the strands keep rupturing on their way up. So that's why we get this kind of step down in behavior. The first observation that we can make is that our concrete remains uncracked for a pretty large range. So we're linear elastic for a fairly large range. And this helps us understand that we can use a linear elastic uncracked behavior assumptions for a pretty large range of moments. So when we're calculating the actual stresses in our pre-stressed concrete member, typically if we use linear elastic material properties, we'll get reasonable results. After cracking, you can see that our slope is going to change in our moment curvature plot. So you can see here the change in slope is caused because our concrete is cracking, either because of the too much applied moment, or I guess too much applied moment in either direction. The next thing that we can notice is with this section, we're actually going to get cracking in the beam when we have no moment applied, or even a small positive moment will have cracking. So this cracking in the pre-stressed beam in this section would occur when you cut the strands and the stress is transferred from the bed to the beam. This isn't good behavior, so we would need to either drape or harp the strands or debond some of the strands to make sure that our beam does not crack under 0 moment. And we'll talk about this later in class. Next, you can see the rounded nature of this moment curvature response. This rounded nature is mainly because of the stress-strain relationship for our pre-stressing strands. So we're modeling the stress-strain relationship of the pre-stressing strands using the Ramberg-Osgood formulation, and that contributes to this rounded nature in the moment curvature response after the concrete has cracked. At the end, at failure of the beam, we can see what type of failure controls the failure of the beam. We can see that the step down is caused by the rupturing of our pre-stressing strands, and this is because we have a large width of our top flange that prevents crushing of the concrete. So we have a failure of our pre-stressing strands rather than crushing of the concrete. So far, we've been looking at the short-term response of our section, But we can also look at the long-term response and account for long-term effects similar to how we did with axial load. What we'll do is for creep, we'll use the effective modulus and include our creep coefficient here. And then wherever we used EC in all of our equations so far, we would use EC effective. For shrinkage, this just affects how the overall strain in our section relates to the strain causing stress in the concrete. So we would just add in the shrinkage strain here. And for strand relaxation, wherever we had EP before, we would now use EP effective. The other item would be our strand rupture. We can increase the strand rupture from 0.04 to 0.054. So our kind of relaxation and long-term effects will kind of increase the strain at which the strand ruptures in our Ramberg-Osgood equation. We can include these time effects in our response 2000 analysis and find our long-term response for our section. If we run the analysis in response 2000, we can again find our average conditions, including tension stiffening, and our conditions at a crack, not including tension stiffening. On this slide, you can see a comparison between the short-term response with and without tension stiffening and the long-term response with and without tension stiffening for our section. So you can see the solid lines are without tension stiffening, and you can see similar, we have our concrete cracking on the top face right here. We have our concrete crushing on the bottom face right here. We have our zero curvature point. We have our concrete cracking on the bottom face right here, and then going nonlinear until we have rupture of our strands again, and then we have a step down as two more strands continue to rupture as we increase our curvature. On the next couple slides, we're going to walk through some of the observations that we can make based on the moment curvature plots for long-term response. The first is that, similar to short-term, our concrete remains uncracked for a very large linear elastic range. And this shows us that, similar to short-term, we can use linear elastic uncracked behavior assumptions for most moments to estimate the behavior and to find the stresses in our section. If we compare the slope of our long-term response to our short-term response, we can see that our uncracked long-term response is going to have a lower flexural stiffness than our short-term response. And this is because the behavior of the beam is mainly dependent, or in this range, the behavior of the beam is mainly dependent on the modulus of the concrete. So for our long-term response, we're using the EC effective or effective modulus, which is lower than the modulus of the concrete. So because of that, we'll have a lower flexural stiffness. Here you can see that the long-term effects are going to lead to a lower cracking moment. So the long-term cracking moment is going to be about 10% lower than the short-term cracking moment. And this is because we're going to lose pre-stress force. So our pre-stressing is going to become less effective over time because of our creep, our shrinkage, and our strand relaxation. The next observation here is you can see that our ultimate strength is going to be about the same for both of our sections. So the long-term effects don't have a significant impact on the ultimate moment. So when we're looking at our determining our nominal moment capacity, we will generally not take into account any of our long-term effects. The last observation between our short-term and long-term response is that with our long-term response, we're going to have a larger ultimate curvature. So this is because we have softer material properties with our EC effective and EP effective, and we also have a smaller strain in the pre-stressing because of our time effects, so it's going to take more strain to rupture our pre-stressing strands. So in short, we'll have a higher ultimate curvature at failure when we take into account our long-term effects. Next, we're going to talk about camber and deflections. Essentially, due to the eccentric or draped pre-stressing tendons, our pre-stressed concrete beams are typically going to be curved upward under no load. This upward deflection that happens, so we'll get some upward deflection, and this upward deflection that happens is called camber. Superimposed loads are going to cause downward deflections, but they need to overcome the upward deflection before we have any kind of negative deflection in the beam. Typically, because of camber, a beam will always have an upward deflection or zero deflection under applied loads. But both the camber and deflection in the beam should be checked. So there are a varying degree of there are a variety of different ways that we can find our deflections. In this section, we're going to talk about one kind of more complex way, and then in future modules, we'll talk about simpler ways that we can find our deflections. In this module, we're going to talk about how to find camber and deflections using moment area theorem with our moment curvature plots that we've been developing. The first step in this procedure is to generate a moment curvature relationship for our given cross-section. If you have the same cross-section along the entire length, then you only need to find one moment curvature relationship. If you have a changing cross-section, so say you have a strand profile that changes along the length, you would need to discretize your beam and then find a moment curvature relationship for each one of your discretizations. The next step in this procedure is to determine your moment diagram based on your given loading and support conditions. So here is a sample moment diagram for a given distributed load and simple supports. From your moment curvature diagrams and your moment diagram, you can find the corresponding curvature diagram along the length of the member. Essentially, you would break up your member into a number of different discretizations and then determine the moment at each point, and then use your moment curvature diagram to determine the curvature under that moment at this point. So doing that, we can figure out our curvature diagram along the length of the beam. We can integrate this curvature diagram with respect to the distance to find our rotation. And we can integrate our rotation with respect to x to find our deflection. This can be more simply done by discretizing the curvature diagram. Essentially, we decide how many discretizations we want to break our curvature diagram into, and then we would assume an average constant curvature along the length of that discretization, and then so we'd have a series of rectangles making up our curvature diagram. And then we can use the moment area theorem to find our deflections. So for a simple support, remember that we would only sum the blow for half of the beam. So here's the equation that you can use if you have a simple support to find the deflections. But again, remember to only do or use half the beam when you're when you're using this summation. So dxi is the distance from the left edge to the center of your layer or of the point of the discretization. Delta xi is the thickness of that discretization, and then this phi I is the average curvature of that discretization there. Next, we will use that procedure to find the initial camber and total deflection of the beam section that we've been working on under a given loading. And now you can pause the video and go to the accompanying video for example problem 3. Next, we'll briefly discuss the crack widths, a relationship between crack widths and spacing. We talked about this already for axial loaded members, and there's a similar relationship between the width of the crack and the spacing of the crack. You can see that in general, if you let cracking happen, then the closer spaced your cracks are, the smaller the width of the crack is. Generally, for pre-stressed members, you want to keep your member uncracked, so this isn't really a concern for us. But if you do allow cracking, you want to make sure that your reinforcement is close to the face, the tension face, and doing this will keep your cracks closer spaced and smaller in width. So far, we've been discussing members with bonded tendons, which means a bonded tendon allows stress transfer between the tendon or pre-stressing strand and the concrete along the length of the beam. This means that along the length of the beam, our strain in the pre-stressing tendon is going to increase and be maximum at the point of maximum moment, and then decrease and be equal to the locked-in strain differential at points when there's no applied moment or axial load. So this varying strain along the length will only happen with bonded tendons. With unbonded tendons, this strain profile is not true. So we'll talk about in the next slide what the strain profile will look like with unbonded tendons. For unbonded tendons, our pre-stressing strain is going to be constant along the length of the strand. And this is because the only point of transfer of stress between the strand and the concrete is at the ends of the beam, or wherever the anchor points are. So what we would need to do is we would need to find the strain in the concrete along the length of the beam, or between anchor points. And then we would need to find the average value of that strain in the concrete between the anchor points. Then the strain in the pre-stressing is going to be equal to that average value of epsilon CP plus our locked-in strain differential. And that value would be the strain value that we can use in the pre-stressing strands. The last topic that we're going to briefly talk about are members with a combination of axial load and moment. So far, we've mainly dealt with members with no axial load applied, but we can use the same procedures to find our moments when we have an axial load applied. We would still use plane sections remaining plane, and we would still use our linear strain distribution based on our top and bottom strains in our curvature and the strain at the centroid of our section. For a particular set of top and bottom strains, we'll get a combination of axial load and moments. So we can analyze the section for a number of different strains to get different points or different axial load and moment points. We can do the procedure with our rectangular stress block, or we can use response, and we'll kind of go through how to use response in an example problem. When looking at combinations of moment and axial load, we'll typically develop a moment axial load interaction diagram. And this diagram represents a series of, or it's a failure envelope. So it represents a series of combinations of moment and axial load that would cause failure of the member that we're looking at. So this is, because it's a capacity and the ultimate capacity is typically controlled by conditions at a crack, when you're developing your failure envelope here, you can ignore tension stiffening. You only really need to include tension stiffening when you're looking at the service behavior of your member and your service behavior after cracking. Now we'll go through a brief example where we'll develop a moment axial interaction diagram for the same section that we've been analyzing using response 2000. So at this point, you can pause this video and go to the accompanying video for example problem 4. We can see here example interaction diagrams for the section that we saw on the previous slide. Here you can see the moment and axial loads, then based on positive or negative bending of the section, and you can see the corresponding curvature. What we can see is that as the axial load increases, our curvature capacity dramatically decreases. So in general, an axial load, a compression axial load will decrease the ductility of our sections. That concludes this presentation on the response of prestressed concrete members to flexure.